Okay, so now I want to teach you about divisibility induction, where the sequence will be increasing by more than 1. Now what I mean by that is typically we're used to the sequence increasing by 1, whereby we go k, k plus 1, k plus 2, and so on. Now, there's going to be occurrences where we can't quite do that. So for example, if the question specifies that this proof only works if it's an even number, can you see how we can't just go 1, 2, 3? We're going to have to go 2, 4, 6. And how do we guarantee that? Well, what we would need to do is go k, then k plus 2 to make sure the next number's even, and then go up by 2 each time, and so on. So this works for both even and odd numbers as well, as you can imagine, because if we start off with an even number and add 2 each time, that guarantees it's even. Whereas if we start off with an odd number and add 2 each time, we guarantee it's odd. The only difference is with even numbers, we'd like to start off with the smallest even number, that's what we try, which is n equals to 2. Whereas for odd numbers, we start off with the smallest odd number, which is n equals to 1, okay? All right, so these questions come into play most frequently when the question specifies that this proof only works if it's even or odd. And this is what you're going to see in the next question. We want to prove that n times n plus 2 is divisible by 4, and you see here, if n is even. So you can see the question has specified that this really only works if it's even. So that means that when we start off with step 1, we want to show it's true for n equals to 2, because that's the smallest even number, yeah? So that's why we start off with that. So substituting 2 into this, we have 2 times 4, which equals to 8, which is indeed divisible by 4. And therefore this is true for n equals to 2. All right, step 2 now. So we make the assumption that it is true for n equals to k, but only where k is even, right? Because here it says only if n is even. So that same rule must apply in our assumption as well. So that means that k plus 2 is divisible by 4 where k is even. So we can say, by making that into an equation, that k times k plus 2 equals to 4m, where m is an integer. Now, moving on to step 3, we want to show it is true for n equals to k plus 2. Now this is where it applies that it's more than 1. It's being increased by more than 1, because usually we have n equals to k plus 1, doesn't it? But here we want to prove that it's true for n equals to k plus 2, because we're increasing by 2 to ensure that it's even. Can you see how that's why we need to increase it by 2? Because we need to ensure that it is even, right? All right, so make sure you write n equals to k plus 2, and then the same process follows. So we write that is k plus 2, which is n just there, and then we have k plus 2, which becomes k plus 4, is divisible by 4. So this is what we want to prove here. And we use this, k plus 2, k plus 4, and looking at that, we can't really do anything with it yet, so we have to expand it. So k times k is k squared, 2 plus 4 gives us 6k, 2 times 4 plus 8. Now, I want us to look back at the assumption first, and that was that k times k plus 2 equals to 4m. So from here, you want to think to yourself, how am I going to manipulate it so I can get k times k plus 2? Yeah? Because we always know we need to use the assumption. So we want to try to find this in here. Now, looking at that, we want to make it into k times k plus 2, which when you expand it is k squared plus 2k. So you can see that we do have this here, but we need to separate the 6k. So we need to separate that into 2k and 4k. And now this k squared plus 2k, I'm just going to substitute 4 for m. So this 4m, I'm going to substitute into here. Yeah, can you see how I've done that? I've separated the 6k into 2k and 4k, and now I've made a k squared plus 2k. I can substitute it for 4m. So now I have 4m there, and I have 4k plus 2 there. So I can just expand that, so they'll become 4m plus 4k plus 8, and that means I can factorize 4 out of that, and that leaves me with 4 times m plus k plus 2, which is divisible by 4. Now I need to double check that this indeed is an integer. So I know m is an integer, and we specified that k is an integer and also true for an even number. So this must be an integer. And the quickest way to do that is go no fractions, no decimals. We can say that's an integer. So if this is divisible by 4, therefore this is true for n equals to k plus 2. So our conclusion specifies that therefore n plus 2 is divisible by 4 for any even integer. Yeah? So we have to specify it is only satisfying this for any even integer.